Part 2 of the Unit 3 practice exam. Number 8, if a spring has an elastic constant of 4.5 times 10 to the 4, what is the energy stored in this spring when it is compressed from its equilibrium position by a force of 10? Okay, are you seeing these things on the screen? So what are we given here? We're given the spring constant, K, E4 meters per meter. We are given a force, 3 newtons, and the question is asking for what is the energy stored. So the question is asking for the elastic potential energy of the spring. And to find out that, we need the x value. How do we get the x value? Well, we have the other formula, Hooke's law, F equals negative kx, and we can get x from this formula because we're given F and K. So x equals F over negative K, 1.5 E3 divided by 4.5 E4. If you divide those, you get 0.033, repeating, meters. And once we know, so that's the distance that the spring is being compressed, and then we can just plug it into this formula. Don't forget to square it, and you're going to end up with an answer of 25 joules, which is A. Number 9. Number 9, a spring with an elastic constant of 4.5 times 10 to the 3. Okay, 4.5 E3 is stretched to a position 7.5 centimeters from its equilibrium position. So you take the spring and you stretch it, so now it has elastic potential energy. What is the increase in energy stored in the spring if it is stretched another 5? So you've got the spring stretched to 7.5, and then you're going to stretch it another 5 centimeters. So it's got even more elastic potential energy right now, and they want to know what is the increase or what is the change. So really what they want is this. The change in energy is going to equal, and the change in anything always equals the final minus the initial. EP, elastic potential final, minus the elastic potential initial. So the initial elastic potential energy was when it was stretched to 7.5 centimeters. And the final is, you can do this in multiple steps. So let's try and do this one in one step. So you stretch it to, let's just draw a little diagram. You stretch the spring to 7.5 centimeters, and then you stretch it another 5 centimeters. So now it's going to be 12.5 centimeters. So the final elastic potential energy of the spring is when it's stretched a distance of 12.5, and the initial is the 7.5. So if you know, if you figure that out in your head, then you can do this question all more or less in one step. Final. Initial. And then if you're mathematically inclined, you may want to factor out the 1/2 and the K. You don't have to. You can just plug all the numbers in. But you can do this also. Oops. You can do it like that if you want. Just makes it a little easier to deal with. And then what's it? 5, 3. The final is the 12.5 centimeters. Make sure you change it to meters. The initial was the 7.5. Make sure you again change it to meters. Stick that into your calculator, and you end up getting the answer, which is, okay, the answer turns out to be 22.5 joules, or D. Okay, so that one requires a little more energy. The next one requires very little. It's pretty straightforward. We have the mass of an electron, we have the speed of an electron, and the question is simply asking for the kinetic energy. So you've got the mass. Mass of an electron is going to be very important in physics 30, and it's actually on the back of your formula sheet. And you have the, okay, no, this isn't as straightforward as I thought. It says, what is the speed? So they're asking for the velocity, but they give you the kinetic energy of 2.3 times 10 to the negative 16 joules. So this is where we're going to take the 1/2 mv squared formula and solve it for V. And as I said in the notes, it's a pretty important formula. It's one of those derivations or one of those manipulations that you may want to just memorize simply because you use this formula quite a bit. Okay, and then it's a matter of just plugging in the numbers. 2 times 3.2 times 10 to the negative 16 divided by 9.11 times 10 to the negative 13. Then take the square root, and you end up getting an answer of, it turns out to be 2.65 times 10 to the 7. Meters per second, which is, just so you know, unbelievably fast. 2.65 times 10 to the 7 is 26,500 kilometers per second. So pretty darn fast. Moving on to number 11. Number 11, we have a mass of 45 kilograms, traveling at 7.5. If the kinetic energy of the mass is increased by, what is its final speed? So this is similar to number 9 in a way, but this time we're dealing with kinetic energy. And they give us the change in energy. So let's just write down our variables. Mass, 45 kilograms. The initial speed, VI, is 7.5 meters per second. And what's this number? It says if the kinetic energy of the mass is increased by, so that's the change in energy. So your delta EK we'll call it, equals 4.5 times 10 to the 3 joules. We want to know what its final speed is. Final speed. And you're just going to use the ever popular delta E or delta whatever equals, whoops, that's a minus. That's an initial. The change in equals the final minus the initial. Now in this question, let's do this one a little differently. Let's just to make this, I think it makes it easier if actually, since you're given the delta E right here, let's find out the EI separately. You don't have to, you can plug everything in and then just solve for VF, but in this case, it may be a little simpler, easier to just calculate your EI by itself, which is simply 1/2 mv squared, right? 1/2 times 45 times 7.5 squared, and that gives you 1,265.625 joules. So that's the initial kinetic energy of the object. And then, so that number can go here if you want, or let's rearrange this first. So We want to get the final velocity, so therefore we need the final energy. So now this is a little easier. 4 times 10 to the 3 plus 1,265.625. This is going to give us the final energy, right? Because we have the change in energy. This is the change in energy. We have the initial energy. So we add those together, and then we'll get the final energy, which turns out to be, what's that going to be? Well, that's 4,500. So it's going to be 5,265.625 joules. Is that correct? So there's the final energy, but we want the final speed. And there is where this formula comes in very useful, because we just kind of memorize this one. It's going to be the square root of 2 times this divided by the mass. Stick all that into your calculator, and you end up getting 16 meters per second. Okay, so that one's D. How are we doing? Let's do one more. Maybe 2 if it's an easy one. No, we'll do one more. This one requires a little more thinking. A proton with that mass and an electron with that mass have the same kinetic energy. What is the ratio of their speeds? The key word here is the ratio. Anytime they're asking for a ratio, then you can just assign arbitrary numbers to, for example, the kinetic energy. Because you're going to look at this question, you're going to say, well, I just have the mass, I don't have the velocities, and I don't have the kinetic energy. Where do I go from here? But since they just want a ratio, and they say that the proton and the electron have the same kinetic energy, what is the ratio of their speeds? So before we actually do the calculation, let's just talk about what kind of answer we may get. A proton has this mass, and this is the mass of an electron. And so the proton is approximately, just very roughly, because this is -27 and this is -31, and 10, the difference between those is 10 to the exponent 4, and 10 to the exponent 4 is 10,000. So just so you know, and you'll need to know this physics 30, a proton is approximately 10,000 times more massive than an electron. Right? So if they have the same kinetic energy, but the electron is 10 times less massive than the proton, then the velocity of the electron is going to have to be significantly bigger. It's going to have to be a lot bigger than the velocity of the proton. So just to get that into your thinking, so that you can say, oh, is this a logical answer that I got this? Okay, now let's go through the process. So we want the ratio of their speeds. And we know the formula for the speed is 1/2, it's because we're solving for velocity, is 2 EKM. And since we're dealing with ratios and they both have the same kinetic energy, what we're just going to arbitrarily say is that the kinetic energy for both of them equals 1. Like, why not? Just make it the easiest number possible. Don't put in 0, because then everything will cancel out. And if they have 0 kinetic energy, then they both have no velocity. So so that makes the question impossible to do. So this is their formula, and we're going to say that the EK for both, because it says they both have the same kinetic energy, is 1. So therefore, the velocity of the proton is going to equal the square root of 2 times 1 divided by the mass of the proton. And when you put that into your calculator, you are going to get 3.46 times 10 to the 13. Okay, meters per second squared if you want, but that's not true actually, because nothing with mass can move faster than the speed of light, and this is the speed of light here. So this number can't actually happen, but we're just asking for a ratio, so it doesn't matter. Then we do the ratio of the electron. Oh, sorry, not the ratio, the velocity of the electron. And again, the kinetic energy is 1, and this is 9.11 times 10 to the negative 31. And if we stick that into our calculator, we get a value of 1.48 times 10 to the 15, which makes sense because we already reasoned that the electron must have a significantly higher velocity than the proton for them to have the same kinetic energies, because the electron is significantly lighter or has less mass. Okay, and then, but they want the ratio. So then the ratio, Vp on top, Ve on the bottom, equals 3.46 times 10 to the 13 divided by 1.48 times 10 to the 15, and you divide those, and you are going to get 0.0234, which is the answer. Which answer is that? There it is right there, 0.234 times 10 to the negative 2. And note, no matter what number you put in here, because you're going to put the same number here, you're always going to get the same ratio. If I put a 2 in here and I put a 2 in here, then this will be doubled and this will be doubled. And when I do the ratio between them, I'm still going to get that. No matter what number I put in here, I could put 10,800,942.682. As long as I put in for both of them, I'm always going to get the same ratio. And that is what allows us to do things like just plugging in random numbers that don't even make sense, because 1 does not make sense here because, as we said, it gives you something that's faster than the speed of light, which, as far as we know, nothing with mass can move faster than the speed of light. But that's for Physics 30. We'll end part 2 right here.